Good morning, everyone. My topic today is container technology, specifically Docker, explained from an operating system perspective. Over the next few minutes, I will show you what actually happens inside the OS when you run a Docker container, how namespace, control group, and the kernel work together to make lightweight visualization possible. Let's get started. Introduction. What is container technology? So, what exactly is a container? Think of it as a package that bundles an application together with everything it need to run, its code, its libraries, its dependencies into one lightweight unit. The key difference from a visual machine is that a container does not carry its own guest operating system. Docker is simplified the most popular platform for building, shaping and running this container. As you can see in this diagram, all containers on a host sit on top of the same host OS kernel and the Docker engine. There are no separate OS inside each container, just the app and its libraries. From the operating system point of view, a container is really just an isolated process. Container versus virtual machine. Let's compare container with virtual machine because this is where the OS level difference become really clear. On the left, a virtual machine sits on top of a Harvis and each VM carries its own full guest operating system along with the app that make VMS heavyweight and slow to boot, often taking minutes. On the right, containers sit directly on the host operating system through the Docker engine. There are no hypervisors and no guest OS. Every container simplifies share that host kernel. That's why containers start in seconds, something even millisecond. We're still keeping process level isolated between apps. OS foundation of Docker. So how does Docker actually achieve this on Linux? It does not invent any new visualization technology. It simplifies architecture for existing kernel feature. First, namespace, which isolate what a process can see. Think like process IDs, network interface, and mount points. Second, control group or C groups, which limit what a process can use, CPU, memory, and disk I/O. Third, unified system, which give Docker its efficient layered image storage. And fourth, Linux capability along with security modules like CLinux or AppMorer, which restrict what kernel level privilege a container actually has. We'll go through each of these one by one, starting with namespace. Linux namespace. Namespace are the Linux kernel feature responsible for isolation. They control what a process is allowed to see. A namespace prep a global system resource so that the process inside it will live. They have their own private copy of that resource. Docker uses six main types PID namespace, so each container see its own process. Three starting from PID1 net namespace giving private network interface and IPS MNT namespace for an isolated file system view. UTS namespace for an independent namespace. IPC namespace for isolated inter-process communication and user namespace for independent user ID mapping. As you can see on the right, even though the host sees these as ordinary numbered process like PID 842, each container itself be live. It's running as PID1 complexity unaware of the other container around it. Control group C groups. While namespace control visibility, control group or C groups control resource usage. This is what stops one container from hopping all the host CPU or memory. C groups let the kernel set limits and quotes on CPU share, memory usage, block I/O, and network bandwidth for a group of processes. For example, if I run a container with the flag equals to CPUs equals to 1.5 and memory equals to 512 minute, the kernel enforces those exact sealing as shown in the brace on the right. And importantly, if a container tries to exceed its limit, the kernel only throttle or kill that specific container through the out-of-memory killer without affecting the host or any other container. Union file system and layered image. Now let's look at how Docker store image efficiently using a union file system. A Docker image is built as a stack of read-only layers. Each layer corresponds to one instruction in a Docker file, like installing a runtime or copying application code. A union file system usually offers on Linux merges all these layers into a single unified viewing for the container. When you actually run a container, Docker add one thin width layer on top while the base image layer underneath remain completely untouched. This is called copy on write, and it's powerful because multiple controllers can share the same base image layer, which saves disk space and make build much faster. Docker architecture. Let's zoom and look at Docker overall architecture, which follow a silent service mode. The Docker silent is the CLI tool you type command into, like docker run or docker build, which send request to the Docker daemon called Docker over a REST API. The daemon is a background service running on the host OS that actually manages image container network and volumes. Underneath, the daemon content and Runec are lower level components that take directly to the Linux kernel to actually create the namespace and C group and start the container process. Notice at the bottom, everything ultimately rests on the host OS kernel. Docker itself doesn't contain any visualization technology. It is essentially an architecture for kernel features that already exist. From image to running process. So let's tie it all together and walk through exactly what happens when you type docker run. Step 1. Docker pull the image, which is fetch and cache on the host file system as layer. Step 2. The kernel create a new namespace PID network mount UDS and IPC specify for the new process. Step 3. C group are attached to the process group applying any CPU or memory limit you specified. Step 4. The union file system mounts the image layer plus a new writable layer. Step 5. The kernel finally executes the container entry point program as PID1 inside its own isolated namespace. The key takeaway here, Docker never boot a new operating system kernel. It simplifies configure the existing host kernel so that one process group gets the illusion of running on its own detected machine. Advantage from an OS standpoint. Give this design. Let's look at the advantage Docker gets purely from being OS native. First, it's lightweight. Since there are no guest OS to boot, container can start in millisecond. Second, high density. Because there are no per instance OS variant, you can run far more container than a VMS on the same hardware. Third, portability. Since namespace and C group behave continuously across Linux distribution, the same container run reliably anywhere with a compatibility kernel. Any fourth, efficient resource use. C group allow fine-grained dynamic allocation of CPU and memory, unlike the fixed per allocate prediction you get with VMS. Limitation and OS level trade-offs. Of course, this OS native design also comes with trade-offs. The biggest one is weaker isolation compared to VMS because all containers share one kernel. A serious kernel vulnerability could portability affect every container on that host. Second, kernel compatibility. A Linux container need a Linux kernel, so it can't run natively on a different kernel like Windows without a compatibility layer or a VM underneath. Third, the noise never problem. If C group are not configured properly, on container can still stab other of shared resource. And fourth, a layer attack surface if Microsoft, for instance, running container in privileged made or genetic it excludes Linux capability can let it directly affect the host OS. Conclusion. To wrap up, Docker containers are not a separate visualization technique, and they are simplified host OS process made to feel isolated. Namespace give us isolation, controlling what a process can see. C group give us resource control, limiting what it can use and a layered union file system make container image efficient to stored share. This OS native design is exactly what makes containers so much faster and light than traditional virtual machine. What the trade-off of sharing a single kernel? Thank you for watching.